Hey, welcome back to Numerical Analysis. So, thus far, for the past month or two, I haven't really been doing any of these MATLAB lectures. We've mainly been covering theoretical aspects of, say, the like Newton's method or the gradient descent method, and now even lately, we've gone as far as doing Euler's method for solving initial value problems. But we haven't sat down and actually gone to the what I'd like to say is the brass tacks of all of this, and is coding it up. This is probably the most important aspect of numerical analysis, and so we shouldn't completely neglect it. So today I'm going to start filling in some of this gap, and one of the things I want to talk about today is what am I going to do today? Numerical differentiation. So this will help you guys out for project 2 in particular, and it's really straightforward to set up. But keep in mind, it's extremely sensitive to noise. Numerical differentiation techniques usually just use 2 or 3 or 4 different points to get an estimate on the derivative at a single point. But what ends up happening is that sometimes you have some noise, and it can just make these slopes be absolutely crazy. And so even when you have numerically generated data, often it can be very hard to recover a good derivative. There are a lot of things that you can do to help this, things like moving averages or other things like that, which we might get into later. There's one paper by Cutts and Brunton that does a good amount of what's called system identification. I think it is, they call it the Cindy algorithm. But there, they take numerical derivatives and then try to fit a polynomial to those, or other kinds of approximations. And they have to do a whole lot of statistical methods in order to get something good out of their numerical derivatives. And so there's sort of a limit to how much you can do with numerical derivatives. And generally speaking, you can't really trust them too far past the first derivative. Maybe you could do 2 derivatives if you have some special relation, but beyond that, you're not going to be able to get very far with noisy data. So so today I'm going to go and run through 2 or 3 different numerical differentiation techniques that we've developed in our class, and we'll see a comparison to how well they do. So hang in there with me, and we'll go ahead and get started. Okay, so welcome back to my office. So here we're going to do some nice MATLAB recording. Here, angle this a little bit closer to knocking into everything. Okay, I can see my computer. What we're going to do is we're going to go ahead and do numerical differentiation routines. And we saw before in the lecture that you can come up with a new numerical differentiation routine if you just sample, say, x minus h, x plus h, x, et cetera, et cetera. You can have x plus 2h, 3h, 4h, 5h, and then you take a polynomial and interpolates those guys, and you take the derivative of that interpolant, not the function itself, and then that'll end up giving you an estimate for the function's derivative, really over that entire interval. But usually we only use that, say, a single point, and then and it's sort of a finite number of calculations we have to do in order to get that derivative. There's the basic one that comes out of straight calculus, which is f of x plus h minus f of x over h, and that's okay, but it doesn't do nearly as well as taking symmetric points, etc. We saw that theoretically in the when we were talking about doing sort of symmetric version of the derivatives, and we looked at the big O notation and the big O constants. And so what I'm going to do today is I'm going to go ahead and code this up. It's only going to take about 15 minutes or so, and then we'll have a routine that you can use for your project. All right, so let's go ahead and jump into it and see what I'm talking about. So I pulled up the last slide from my lecture on my tablet here, so I can sort of work concurrently on all these things, and I'm basically going to code up these guys. And so what this is all going to end up being is open, there. So everything that we're going to end up seeing is more or less going to be a shift. We're going to take the data, and in order to get f of x plus h, we're going to shift the data back 1. And in order to get f of x minus h, we're going to shift it forward 1. That means that we're going to end up losing the point at either endpoint, because there's at the very left endpoint there's no minus h in order to work with, and at the right endpoint there's no plus h to work with. So we're going to end up having, so we're going to have to end up throwing out those points if we just stick to the same routine. You could separately do those very individual points with a different numerical differentiation routine that is one-sided. So you can do, just for the first point, you can do f of x plus h minus f of x over h, and that'll give you an estimate there. And yeah. But so what we're going to do is we're going to code up two different functions. So numerical differentiation. And we're going to come up with two functions. We're going to come up with a function that we want to take a derivative. So we have our function f here that I'm going to define sort of in line. And so I'm going to say f of x equals x at x. And so you just put in your favorite function. So I'm going to say x squared, I would say, yeah, x squared plus sine of x, say 3 sine of x, sine of 3x. And just for comparison, I'm going to have what I'm going to call f diff, and so we're just going to take the actual derivative of this. Usually you won't have access to this when you're given data, but we want to be able to compare this for just see how well we're doing. So it's going to be 3 times cosine of 3 times x. Okay, and so now we need to generate our data. In order to do that, I need to come up with my t's. So t is going to run from, say, we're going to let it go from 0 to 0.1, and we're going to go all the way up to, say, 3. Instead of 0.1, I'm just going to actually make h as being my step size. And so h is going to be, we'll set that to be 0.1, and inside of here, I'm just going to put h. That way we can adjust h and see, you know, if we have higher resolution to our data, if we get better derivatives versus if not. And if I forget to do that by the end of the lecture, sorry. But yeah, there we go. So then we need to come up with get the data itself. So I'm going to say y is equal to f of t, right? And if I did everything right, then I should be able to get 2 different vectors of data. And no. So we have an error using the exponential. I'm going to put a point here, and so now hopefully that'll end up working. So it's going to be entry-wise exponentiation rather than just trying to take a vector and exponentiate it. That's what I had a problem with. And so I'm going to go ahead and do that. Boop, got something. So I'm going to go ahead and make a figure. I'm going to say plot t comma y, and let's see what we get. Boop. There we go. Okay, so it's increasing as we go up. Remember, it's a quadratic function, and then we'll also have a sinusoid that's sort of making it do funny things. Yeah, okay. Let's see. I'm going to put a diff y. It's going to be f diff of t. All right, so now we have 2 different plots. And so if I go in here, I say figure. I want to say plot t comma diff y. Let's see what we get. Okay, so that's our derivative that we're working with. All right, so this is the exact derivative because we know the actual form of the functions themselves. And so this is not really a realistic data situation. You're usually not going to have access to this. But what is nice about this sort of approach is that it allows us to have sort of a benchmark to compare our algorithms against. So we can see explicitly what the error is going to be rather than sort of like, we know big O, it should be better, you know, something like that. So this is going to end up being really nice for us. Okay, so all right, so that's accumulated data, and now let's come up with our different differentiation routines. Now, MATLAB does have a differentiation routine. I think it's just diff, so I can say help diff, and it's going to give us you know, sort of the different commands we can put in for differentiation. So here it's difference and approximate derivatives, and so I could just take this and we'd be done. But truly, it's not going to do anything really different than what we're doing, and it's good to know how to do this on your own. But if you want, just for the sake of being a mature MATLAB user, you should know that there is this function in there, even if we don't explicitly use it. So let's go ahead and take a look at the first method. So if we take a look at my tablet, we have f of x plus h minus f of x divided by h. All right, and that's going to be our first attempt at a numerical derivative, and this is straight out of Calculus 1. We didn't need we didn't need a whole class on numerical analysis to pull this guy out. So let's go ahead and give it a shot. So f of x plus h. So x is going to be the current time point that we're looking at, and x plus h is going to be the one that's immediately afterwards. So what we're going to do is we want to shift our data points over a little bit. So I'm going to say, we have our y, and now I want to subtract. So I want to get the next point after that. So I'm going to take a look at just y from 2 to the end, and I'm going to take and subtract off y from 1 to the end, minus 1. I think I got all that right. Yeah. And so this is going to be, so the first entry of this guy is going to be at a y of 2. And then it goes y of 3, y of 4, etc. And this one's at y of 1, y of 2, y of 3. And so so when you take these two vectors and you just stack them on top of each other and you take the difference, you're going to get exactly this. And so what we're missing now is just our h. And so I'm going to take this quantity and I'm going to divide it by h. And then I'm going to say, I'm going to call this new vector that we get, it's going to be differentiation 1. Okay, so what we have here is our first attempt at this, and notice that the vector itself ends up being one entry less than the other one. And so I'm going to call diff t is going to be t running from 1 up to n minus 1. Okay, so the only reason I'm doing this is because when we plot these things, I try to use t, it's not going to work. And the reason why it's not going to work is it's expecting to have these sort of extra, it's expecting to have as many entries as are in here, but we've just shaved 1 off. So I'm shaving 1 off here. So let's go ahead and give this plot a try. So I'm going to say figure. So first we're going to plot. We don't care about y so much as far as the comparison goes, and so we're going to take diff y, and I'm going to say hold on, and then I'm going to go ahead and I'm going to say plot diff t and differentiation 1, right? And so I'm going to say hold on, and I want to put a title, and so I'm going to say calculus 1 numerical differentiation. And see how that works out. And so hold off, put that off, and now we should be good. So if I push play, it should go something. Okay, so that's pretty good. It looks a little shifted off here. And maybe I just trimmed the wrong t. So if instead I look at 2 up to end, let's see what we get. Should line up maybe a little bit better. Okay, not really. Let's put it back. I think that was a better choice. So yeah, so what do we get? We see that we're actually pretty close here. But it's not perfect. I mean, like, just look at that. I mean, like, the peaks are off, but that's fine. The shape is more or less okay. And so it looks sort of like a delayed version of everything. And yeah, so let's go ahead and compare the errors. So I'm going to say figure, I'm going to plot. We're just going to plot. We want to plot both of them, and remember they both are different lengths. So I'm going to say, I'm going to use diff t, and I'm going to go with diff y, and we're going to go from 1 up to n minus 1 for diff y. And we want to take sort of the absolute value of these two guys, and what do we get? So it's going to be differentiation 1, and yeah. So let's see. So I'm going to say hold on, and I'm going to say title. We're going to say error from the first method. Okay, and hold off. Okay, let's give it a shot. Going to push play. Boop. There we go. So that's the error. The error is 0.5, which, you know, in the end, I mean, when we're going all the way up to, you know, as high as 8 is the absolute value of the largest value that we have is at, like, say 7.5 or so. 0.5 isn't terrible, but I mean you can see, I mean, it's pretty close. But we would really hope we can get a lot better than that. Usually we want to get down to like less than 5% error if possible, and so this is yeah, much larger than that. But okay, so one thing we can try is we can try to reduce the step size. So if I change this to 0.01, and we can see what we get. All right, so now I've already, by decreasing the step size and make it 1/10 of what it was before, we see that we've actually improved our differentiation error by nearly 10 times. And this coincides exactly with what we expected. Remember that this method is a big O of H method, so if you change H by a factor of 10, you should see a factor of 10 change in the error itself. And so that's what we just saw here. And if we want to go really crazy, and we see that we're practically matching up here, and if we want to go really crazy, we can do another one. This might actually take a second. And so now we see that we get like 10 to the minus 3. But, you know, it might not be realistic I mean, so you can see we practically have perfect alignment here. But the thing is, it's not necessarily practical in order to expect a 1/1000th, hertz sampling rate. So this is so like maybe 1/10 might be more realistic. I know EEG equipment does samples at like, I think 200 hertz, maybe like 250 hertz, you know, something like that. And so so yeah, 1000 hertz is really sort of out of the question. But you should be able to do, so we're going to try to do better with less. And so rather than doing 1000 hertz and having that many samples, that's a lot of data to hold on to. We're going to try to hold on to, you know, something. We're going to try to work with something a little bit smaller. So here we're going to stick down to the sort of 10 hertz sampling rate, assuming t equals 1. T is measured in seconds. And then let's see what we have. So let's go for differentiation 2. So this one is going to be, so we have f of x plus h minus f of x minus h, and we're dividing this by 2h, right? And so this is our symmetric version, and this is one we expect to perform best out of the ones that we talked about in the lecture. So if we want to get this guy, we first need to go with the one shifted guy. So we have y of 2 to the end, so starting at 2 and going forward. And then we want to subtract y of going backwards, so we're going to go minus 1 to end minus 1, right? But obviously there's something wrong here. We don't have those points to start with, so we can't start at 1. Instead, we're going to start at y of 2, and then we're going to use 1, etc. So this is going to start at 3, and we're going to start at 1. And since we shifted up by 1, 2 here, we need to end by shifting, truncating it here at the end. So at either endpoint, we have issues because we don't have a -1 data point, and we don't have a data point at end plus 1, right? So we have to kill sort of 2 points on either end. In the end, at the end of the day, you know, the sacrifice, if you have enough data, isn't going to be that big of a deal. But if you only have a few data points, like 3 or 4, then I mean, obviously you can't use this method. So we're going to take this and we're going to divide by 2h. And what I'm going to do now is I'm going to take this guy and I'm going to go ahead and I'm going to add a plot to it. So I'm going to take this plot, I'm going to copy it and here, and I'm going to have it say differentiation 2. So this is going to be diff t2. We're going to have to truncate time twice now. And so we're going to say diff t is equal to t, which goes from 2 to n minus 1. Right? So we have to chop off the left and right endpoints, and so that's what we're doing here. Okay, and so we're going to go from 2 to n minus 1, and there, those should work out. So I want to make sure I label these guys. So I'm going to say display name, and we'll say experiment 1. And then for the second one, I'm going to display name experiment 2, and then we'll just add on hold on, and we'll put on legend. Okay, so there we go. Now from numerical differentiation. Okay, so let's go ahead and give it a shot. So just so we can get another plot of not just the error, we copied that already, but let's see what the derivative looks like, sort of qualitatively. So I'm going to go ahead and add, just copy this figure, and I'm going to take a look at diff t2, and that should be 2 here, and I'm going to take a look at differentiation 2. Okay, so symmetric, and so this is the symmetric version. Okay, so let's see. Oh no, we have an error. Missing or unbalanced brackets. Oh, right, and 2h. I can't really do that. There we go. Okay, so let's give it a shot. Boop. All right, so this is what it's supposed to look like. I'm not sure exactly which figure that was. The title didn't show up. Oh. There, okay, I had an error. Sorry. Let's see. So differentiation. There was some typo. Okay, now let's do it. All right, and it still didn't give us our title, which is frustrating. Okay, still have an error. All right, let's check it out. On line 33, there we go. I don't know what I was doing. Oh, I see. I'm copying over my typo. There we go. So, push play. All right, everything should be working. Whew. Okay, so we see that using the same data points as we had for this guy, this one we ended up having this sort of error that was coming on here, and now we see that if we use the symmetric version, we actually get pretty close with just the 0.1, so this 10 hertz signal, and so that's a vast improvement, and that really shows you right here why people like the symmetric method better. And here you can see that we went from using the same data points, we went from having an error that was up at 0.5 in absolute value, 0.5-ish, all the way down to something as low as 0.04. And so, in order to get that, we actually had to increase the samples by 10 times. And so, really with the 0.1 sampling, we're already doing dramatically better. And so this is something that we were really hoping for. So if I go ahead and take, if you want to see how much better it does, we put 0.1, man, I mean, look at that. You can't even, there's not even a comparison. So it's 0.0004. So in this case, we saw, just like what we expected, it should be a big O of h squared for the symmetric method. And so we see that there's been such a dramatic drop by doing it. It decreased h by 0.1, divided by another 10, and the error has decreased by a factor of 100. And so, and here you already see no difference going on here. And so this shows you that, given certain data points, you can take advantage of that data point, those data points, in much better ways if you choose the right method. So that's good. Now I'm going to switch this back to 0.1 so we can actually see some errors coming out of here. And we have one method left to do, and that is the sort of one-sided numerical differentiation technique. So there's one last one, which is, say, f of x plus 2h minus f of x, and this is divided by 2 times h, right? And parentheses there. And let me double check. Yep, that's what it is. And so let's go and do this. So this is going to be differentiation, we'll call it 3, and we're going to have y of, now, x plus 2h is going to start at 3 and go up to end, and then we're going to have, we're just using f of x, so it's going to be starting at the first one, and but then since we need these two to have the same length, we're going to have end minus 2 here. So it's the same number of points that we're using, the same length of a vector that we're using for the symmetric method, but for the one-sided method, it actually starts at y1 with this term here. So I'm going to divide this by 2 times h, and then let's go ahead and take a look. So I'm going to put this in here, boop, and so I guess I'll just say diff 3. What is this going to end up looking like? So this is going to go from 1 up to end minus 2 to match up with this guy. All right, so so here we're going to have diff t3, and we're going to have differentiation 3, and this is sort of the one-sided numerical differentiation routine. And then in here, I'm going to go ahead and add yet another plot. And so we're going to have diff 3, and we're going to take a look at y, which is going to go from 1 to end minus 2, and we're going to subtract off differentiation 3. And so this is experiment 3. Okay, so let's push play and see what we get. Okay, so so the one-sided numerical differentiation, it's definitely not looking as good as what we hoped it would. It's okay. I mean, not really. I mean, like we actually our first order numerical differentiation routine with the same points ended up being a lot closer. But at the end of the day, experiment 3, yeah, that's terrible. It's worse than what we actually started with. So, but we hope that as I decrease the h step size, that we end up actually improving on this, and so maybe this is sort of a big O constant problem. So if we know that the routine itself is actually big O of h squared, but if you have a bad big O constant, until you get h small enough, it might still be giving you a really large error. We are hoping it would work something like this, and so hopefully as I decrease the step size, it's actually going to get better than, say, this guy, our regular numerical differentiation from Calculus 1. If you can't beat your Calculus 1 method, then there's a problem. Okay, so let's go ahead and take a look. So I'm going to go ahead and decrease step size by a factor of 10, and let's see what happens. Okay, so experiment 3, still not great. Experiment 2, boom, it's practically flat, and the regular numerical differentiation is still winning. So let's see if we can decrease it again and see at what point we end up start winning. And no, we're not winning here either. So yeah, that's not the greatest thing. Let's see, another one. Boop. It's gotta start taking longer and longer. Yeah. That is big O h squared, right? Yeah. Yeah, we worked that out. Okay. Yeah, not great. And so let's see. Maybe there's other things we can do in order to improve it. So let's get back to square 1, where we had just 10 hertz sampling, and that's basically back where things were. Let's see if I instead shift these points around. It's sort of cheating a little bit. It's sort of like fudging your numbers in your calculus exam. But let's go ahead and see what we get now. And it still didn't improve it, even with this fudging. And so, yeah, no. All right, the one-sided derivatives, out. We do not want to use those. Might as well just stick with your regular calculus 1. Of course, you can do higher order ones, and those will improve your performance. But yeah, so that's numerical differentiation. The only thing that I can do after this point is we can actually talk about what happens when you add noise. And so I'm going to come up with a signal, and so just to give you an example of what you do to find noise. So there's this rand function. And so let's say rand of 2, what does it give me? It gives me a 2 by 2 matrix of random numbers between that take values between 0 and 1. And I can give us a vector if I just say 1, 2. So this gives us sort of a row vector of just 2 samples of some random numbers. So what I'm going to do then is I'm going to take y, I'm going to add some noise. And so I'm going to take y noise. I'm going to say y plus random of 1 to length of y. And how big do I want my noise to be? Let's start small and we'll say 0.01. All right, and so now we'll start our noise plots. And so let's see. So we're going to come up with, we're going to use these 3 different differentiation techniques here. So we have differentiation 1, which was sort of our calculus 1 version. And I have differentiation 2, which is our symmetric one. And I have differentiation 3, which is our really horrible one-sided derivative. And instead of y, I'm going to go ahead and replace all these with y noise. Well, let me just type noise here and I can copy that. So noise. Right, so I'm going to put it here, y noise, y noise, y noise, y noise, and y noise. All right, now let's go ahead and plot all the noise. And so I'll call these guys, noise derivatives 1, noise derivative 2, etc. So noise, 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 put that here, noise, noise, and noise. Okay, so I'm keeping this here. So this is the original function that we know the pure derivative of. And now I'm going to try to compare the different methods and how close they get in the presence of noise. This is going to be terrible, but let's go ahead and take a look. So go ahead and press play. Error from numerical differentiation. This is with noise, and this is without noise. I see it actually didn't do too bad. So still, symmetric version is winning out over everything. Regular calculus didn't do too bad, and etc. But now, why don't we see what actually happened to the signal itself? So I'm going to say figure. I'm going to say plot t with y noise, and then I'm going to say title. Hold on, sorry. And title is going to be signal with noise. So this is what we'd actually call signal noise. So it's noise that would hit the signal itself. So it's probably like some sort of cut out. I didn't realize the video cut out, but I don't have a whole lot of time. But yeah, let's go ahead and see this. So hold off, and there we go. And yeah, let's see. Boop. And so that's a noise. Signal with noise, can't see anything, right? That isn't too much of a noise. And so no wonder it's working pretty well. But now let's say that we have a much larger noise component. And now we start seeing like really bad errors coming up. Our symmetric method is even doing poorly at this region. And but you still don't see too much noise going on here. And so if I decrease the step size so we can see more noise coming through, this is what we end up having. So we see that we have up to a factor of 4 from some of our methods here. The first one is doing pretty bad. Experiment 3 actually is performing not too bad in this case. And so it looks like in the presence of noise, using the one-sided method, I actually didn't do too bad. Symmetric method seems to be floating around there, same as the one-sided method. And so, but what's significant here is that the noise doesn't look that bad. I mean, like, it's just a little bit of wiggles. But our numerical differentiation routines can be off by as much as like 4. And that's a tremendous difference. And so, so that's So that's sort of a lesson there. Once you have noisy data, a lot of these numerical differentiation techniques, which work almost perfectly in like a clean data sort of situation, are going to have some issues. And this isn't even that noisy of data. So, so there's things you can do. You can smooth out your function using, say, a moving average filter, which will help fill out those bumps, and you can be able to regain some of these guys. There's other things like Kalman filters and other things like that that will clean up the noise even better. But yeah, anyway, battery on the camera is running out, and it's probably a good time to stop. Thanks for hanging in there with me, and this is Numerical Differentiation, and you're watching That Math Thing. All right, take care. Okay, so I hope you liked the lecture and it helps you guys with this numerical differentiation routine, and yeah, I just want to make this end of this class be as easy and straightforward as possible for everybody. Most people in the class are doing okay, and I just want a smooth exit, especially in this pandemic. I'm not trying to do anything tricky or scary for the class. So yeah. In any case, so I'm going to follow this up with 2 other lectures, and on, say, Newton's method and gradient descent and things like that, and yeah, and hopefully this will round out a lot of the missing bits out of my out of the MATLAB segments for the class. In any case, thanks for watching, and I'll see you next time.